Hello students, how are you all? In last class you learned occurrence, atomic properties and physical properties of group 17 elements. The today's topic is chemical properties of group 17 elements. In that first one, oxidation states of group 17 elements. First one, oxidation states. So I am taking halogen atom. Taking halogen atom. I am writing the general electron configuration of halogen atom. The general electron configuration is Ns2 Np5. The general electron configuration of halogen is Ns2 Np5. I am taking Nd0. That means no electron in d orbital. There is no electron in d orbital. Nd0. So d orbital is absent in the fluorine. So this is general electron configuration of halogen atom Ns2 Np5 Nd0. No electron in the d orbital. Next, this is ground. I am taking ground state electronic configuration. That is ground state electronic configuration. This is ground state electronic configuration. In the s orbital, ns orbital, there are 2 electrons. Clear? In the p orbital, np orbital, there are 5 electrons. 1, 2, 3, 4, and this is the 5th. So np orbital has 5 electrons. Nd orbital, there is no electrons. Nd0. There is no electrons in the Nd orbital. So by looking at this electron configuration, what is the point we understand is in the Np orbital there is a one unpaired electron is there. This one unpaired electron is account for -1 and +1 oxidation state. One unpaired electron, one unpaired electron account for -1 or +1 oxidation states. -1 or +1 oxidation state. So this one electron present in the Np orbital, this electron account for -1 or +1 oxidation states. So all these elements exhibit -1 oxidation state. All group 17 elements exhibit -1 oxidation state because they are short of one electron to reach octet configuration. What is my point meaning is I am taking Ns2 Np5 general electronic configuration. By looking at the general electron configuration, what we find is there are 7 valence electrons. 2 plus 5, the total number of valence electrons is equal to 7. And they reach noble gas configuration, nothing but octet configuration. They reach noble gas configuration by gaining one electron. If they gain one electron, they will reach noble gas configuration. They are shortage of one electron to reach octet configuration. So that they will gain one electron. Gaining of one electron will get a negative charge, one negative charge. So all these elements are shortage of one electron to reach octet configuration, so that all these elements gain one electron. As a result, all these elements exhibit -1 oxidation state. So the -1 oxidation is because of the noble group 7 elements are shortage of one electron to reach octet configuration. So the gaining of one electron will get total number of electrons will become 8. 7 plus 1, 8 electrons. So that they will exhibit -1 oxidation state. This is the first one. And the electron present in the Np orbital get excited to the Nd orbital. Next, excitation. So first, this is the first excitation. First excitation. The first excitation, these Np orbitals remain, Ns orbital remains the same. Then Np orbitals. Sorry, Np electrons. Ns electrons remain same. Np electrons. So one electron is jumping here. Then the remaining number of electrons is 4 only. 1, 2, 3, 4. One electron is jumped to here. As a result, then the configuration is Nd0 will become Nd1. By looking at this, what the point we understand is how many number of unpaired electrons. In the first case, only one unpaired is there. Look at here. So this is one unpaired electron. Here is second one. Here is the third one. There are 3 unpaired. there are 3 unpaired electrons. So 3 unpaired electrons account for plus 3 oxidation state. All these elements exhibit except fluorine. Fluorine exhibit minus 1 only. Remaining elements exhibit plus 1, minus 1, plus 1, plus 3, plus 5 and plus 7. So mainly minus 1, plus 3, plus 5 and plus 7. These elements exhibit minus 1, plus 3, plus 5, plus 7. Here the plus 3 oxidation state because of the presence of 3 unpaired electron. So fluorine cannot show plus 3, plus 5, plus 7 oxidation state because it do not have any d orbital. Because of absence of d orbitals in the fluorine, it exhibit only minus 1 oxidation state. It cannot exhibit plus 3, plus 5, plus 7. So fluorine exhibit only minus 1 oxidation state. So the point is due to these 3 unpaired electrons, they exhibit plus 3 oxidation state. 3 electrons, 3 unpaired electrons, 3 unpaired electrons account for plus 3 oxidation state. Plus 3 oxidation state. Next, this is the first excitation. I am taking second excited state. Second excited state. Second excited state. This ns electrons remains same. And the point is here is paired electron is there. This electron will be jumped to the d orbital. The number of electrons will become 3 only. This electron is jumping to, this electron is jumping to here. As a result, then what we are going to get is a d2 configuration. So 1. So by looking at then how many number of unpaired electrons present in this orbitals is 1, 2, 3, 4, 5. There are 5 unpaired. 5 unpaired electrons. These 5 unpaired electrons account for plus 5 oxidation state. They exhibit plus 5 oxidation state because of presence of 5 unpaired electrons. 5 unpaired electrons. 5 unpaired electrons account. 5 unpaired electrons account for plus 5 oxidation state. Plus 5 oxidation state. So next, third excited state. Third excited state. That means the electron present in this s orbital, ns orbital also will be jumped to the next jumped into the d orbital. Then configuration will become only one electron in the ns orbital. Then here is 3 unpaired as usual, 1, 2, 3, and there are 3 unpaired electrons in the d orbital, 1, 2, 3. Look at here. So here is first electron is excited, then we get the first excited state, and electron, this is the first electron jumped from np orbital to nd orbital. This is the second electron jumped from np orbital to nd orbital. This is the third electron jumped from ns orbital to ns orbital to nd orbital. So how many number of unpaired electrons we got is 1, 2, 3, 4, 5, 6, 7. The total number of unpaired electrons is 7. 7 unpaired. 7 unpaired electrons. These 7 unpaired electrons account for plus 7 oxidation state. 7 unpaired electrons account for plus 7 oxidation state. Plus 7 oxidation state. So all these elements exhibit plus 3, plus 5 and plus 7. So minus 1, plus 3, plus 5, plus 7 oxygen state, the plus minus 1 and plus 1 because of presence of 1 unpaired electron, and plus 3 is because of presence of 3 unpaired electrons, and plus 5 oxygen state because of presence of 5 unpaired electrons, and plus 7 is because of presence of 7 unpaired electrons. Now another important point is chlorine and bromine. Chlorine and bromine even can exhibit plus 4 and plus 6 oxidation states also in their oxides and oxo acids. They can exhibit plus 4 and plus 6 oxidation state in their oxides and oxo acids. And another important point is fluorine can exhibit only one oxidation state, that is minus 1. The fluorine can exhibit only minus 1 oxidation state. It do not exhibit plus 3, plus 5, plus 7 because absence of d orbital. The fluorine do not have any d orbitals to expand this oxidation numbers. To expand the oxidation number, it do not have any d orbital. So due to absence of d orbital in the fluorine, it do not exhibit plus 3, plus 5, plus 7 oxygen state. Fluorine can exhibit minus 1 only because of its high electronegativity. So these are the oxidation states of group 17 elements. Next, all halogens are highly reactive. Next point, all halogens are highly reactive. All halogens are highly reactive, and the reactivity decreases down the group. That means the reactivity order, fluorine is greater than, chlorine is greater than, bromine is greater than iodine. So the reactivity order of halogens is fluorine, chlorine, bromine, iodine. This is the reactivity order of halogens. Next, all halogens are strong oxidizing agent. They have a strong oxidizing nature. Halogens has strong oxidizing nature. So oxidizing nature because of they are ready to accept electrons. I already said they have ns to np for electron configuration. They are only 7 valence electrons in the valence shell. As a result, they are short of 1 electron to reach octet configuration. So they are ready to take electrons so that they behave as a strong oxidizing agent. So they are halogens have strong oxidizing nature due to ready to acceptance of 1 electron. Next, in general, halogen oxidizes halide. Halogen oxidizes halide ion of higher atomic number. Halide ion of higher atomic number. So what is this point meaning is I am taking fluorine. So fluorine, and another halogen I am taking X to X minus. Any halogen you can take. This X maybe you can take chlorine, bromine, iodine. So here fluorine is a halogen, this X also is a halogen. So both are halogens only. So in general, halogen oxidizes a halide ion of a higher atomic number. So this fluorine is the lower atomic number when compared to the chlorine, bromine, iodine. Now let's look at the reaction. What we'll find is 2F minus F2 will become 2F minus plus 2X minus become X2. So 2F minus plus X2. So what is this point meaning is let us take one example for understanding. I am taking fluorine F2, in the place of X I am taking chlorine. First I am taking fluorine, in the place of X I am taking chlorine, 2Cl minus. Then the product is 2F minus plus Cl2. Look at this. Oxidation number of fluorine is 0. Here oxidation number of fluorine is what? Minus 1. So 0 to minus 1. 0 to minus 1 in the sense oxygen here is it is nothing but reduction. Here is chlorine is minus 1 and elemental state chlorine is 0. Minus 1 to 0 number is increased. Increasing oxidation number is called as oxidation. oxidation. So what the point we understand from is fluorine can oxidize chlorine, bromine, iodine. So fluorine is a strong oxidizing agent. Fluorine is a strong oxidizing agent. Even it can oxidize other halogens, chlorine, bromine, iodine. So fluorine is undergoing reduction and making other substance is oxidation. The substance itself undergo reduction. The substance itself undergo reduction. Make other substance oxidation is called as oxidizing agent. Here fluorine is the strongest oxidizing agent. Even it can oxidize chlorides, bromide and iodide ions, so Cl, Br, I minus. So halogens it can oxidize of higher atomic number. So next I am taking chlorine next. I am taking chlorine, Cl2. Cl2 plus 2x minus. In this case x is equal to what we can expect, what is the statement in general? Halogen oxidizes halide ion of higher atomic number. So here x is here chlorine is we took, this x must be atomic number greater than the chlorine. What are the elements we have? One is bromine and second one is iodine, isn't it? So bromine and iodine. Then what is the product we can expect in this case is Cl2 plus 2x minus then 2Cl minus plus we are going to get here is x2. This x2 will be get Br2 or I2. I think you got what I mean is. Then if you want to take one example, I will take. So Cl2 plus 2Br minus. 2Br minus. Then what is the reaction we can expect here is 2Cl minus plus Br2. Br2. So look at this. Chlorine oxidation number is 0. Here is minus 1. Minus 1. And here is bromine oxidation number is minus 1 and bromine here is 0. This is nothing but what? Increasing oxidation number, oxidation. This is nothing but what? Reduction. Here is chlorine undergoing reduction and making bromine is oxidation. So chlorine is a oxidizing agent. Of course all these halogens are oxidizing agent and the point is the halogen oxidizes halide ion of higher atomic number. So chlorine can oxidize bromine, iodine. I think got what I meaning is. Then next one is Br2 plus 2I minus gives rise to 2Br minus plus I2. So look at this equation. Here is bromine can oxidize I minus. Here oxidation number of bromine is 0, elemental state. Here bromine is minus 1. So look at this 0 to minus 1 nothing but this is reduction. Decreasing oxidation number is reduction. His iodine is minus 1, elemental state is 0. So minus 1 to 0. This is nothing but oxidation. Then what is the point to understand is bromine itself undergoing reduction, making iodide ion I minus oxidation. So that bromine is a oxidizing agent. So in general statement, in general halogen oxidizes halide ion of higher atomic number. Here is this iodine is a higher atomic number when compared to the bromine. So that is a general statement. So fluorine can oxidize. What is the conclusion is fluorine can oxidize chlorine, bromine, iodine. If you take the fluorine can oxidize chlorine, bromine, iodine. So fluorine can oxidize these three, and the chlorine can oxidize bromine and iodine, and the bromine can oxidize iodine. So general statement, in general halogen oxidizes halide ion of higher atomic number. Next, the relative oxidizing power of halogens. The relative oxidizing power halogens. The relative oxidizing power of halogens can be explained by the reaction with water. The relative oxidizing power of halogens can be explained by the reaction with water. First I am taking a fluorine, F2. So F2 is a gas plus water is liquid. Then the products are F minus plus O2 plus H plus. So we have to balance it. Here is oxygen is liberated. I am taking 2H2O. 2H2 in the sense of 4 hydrogens. This will become 4HF. Then 4H plus. This will be 2F2. This will be 4F minus. 4F minus 4H plus. Now look at this case. Here is this is in aqueous. O2 is a gas. This is in aqueous. So here fluorine can oxidizes. Fluorine oxidizes water into oxygen. So water is converting into oxygen. Fluorine can oxidize water into oxygen. First reaction. Second, I'm taking chlorine and bromine. Here X is equal to chlorine and bromine. X is equal to chlorine and bromine plus water H2O. The point is chlorine and bromine react with water, do not oxidize the water. Fluorine is oxidizing water into oxygen, but chlorine and bromine do not oxidize the water, but they will react with water. Then the products are HX, we are taking X plus one more product is HOX. The products are HX and HOX. This is a liquid, it is in aqueous, it is also in aqueous. Look at this, what are the products formed is hydrohalic acid. Hydrohalic acid and this is hydrohalic acid and this is hypohalous acid. So here chlorine and bromine react with water, produce hydrohalic acid and hypohalous acid, but fluorine is oxidizing water into oxygen. One difference is there. Next I'm taking iodine. So iodine do not react with water. Reaction of iodine with water is a non-spontaneous. The reaction of iodine with water is a non-spontaneous. That means reaction is not possible. So iodine do not react with water, but the reverse reaction is possible, what we observed in the fluorine case. So reverse reaction is possible. So how to write the reverse reaction is I'm taking I minus plus O2 plus 4H plus, exactly opposite reaction we can take. Then 4I minus plus O2 gives rise to the product is I2. 2I2 solid plus 2H2O. This is liquid. Exactly opposite. What is the reaction observed in the case of fluorine? Opposite reaction we can expect in the case of iodine. Now the point is the relative oxidizing power of halogens. Fluorine can oxidize water into oxygen. So first point, fluorine can oxidize water into oxygen, and chlorine and bromine do not oxidize the water, but they will react with water forming hydrohalic acid and hypohalous acid. So hydrohalic acid and hypohalous acid, and the reaction of iodine is non-spontaneous with the reaction of iodine with water is a non-spontaneous. Reaction is not possible. Reverse reaction observed, what we observed in the case of fluorine. Now what we conclude is fluorine is a strong oxidizing agent, very strong oxidizing agent. Even it oxidize the water into oxygen, and chlorine bromine are reacting to water. Iodine reaction is not possible. So this is the relative oxidizing power of halogens. So this is reactivity of halogens. Halogens are highly reactive. The reactivity of is fluorine, chlorine, bromine, iodine. While moving from top to bottom, the reactivity is decreases. That means fluorine is more reactive, chlorine is less reactive, and halogens are strong oxidizing agent. Then in general, halogen oxidizes halide in a higher atomic number also, because this is the reactions, and the relative oxidizing power of halogens is fluorine is a strong oxidizing agent. So this is the oxidizing nature of halogens. Next, anomalous behavior of fluorine. The fluorine differs from the rest of the elements of this group is due to, the first one is its small size. The fluorine differ from rest of the elements. Rest of the elements of this group. Rest of elements of this group due to, first reason, due to its small size. Due to its small size. So the fluorine differs from the rest of the elements of this group due to its small size, nothing but anomalous behavior. The second one is it highest electronegativity. Highest electronegativity. The third one is low FF bond dissociation enthalpy. Low FF bond dissociation enthalpy. This is the third reason. And the fourth one is non-availability of d orbital in the valence shell. Non-availability of d orbitals in the valence shell. So non-availability of d orbitals in the valence shell, these are the reasons because anomalous behavior of fluorine. The anomalous behavior of fluorine is because of its small size, highest electron negativity, and low FF bond dissociation enthalpy, and the last one is absence of d orbital or nothing but non-availability of d orbitals in the valence shell. So this is anomalous behavior of fluorine. Next, reactivity towards elements. In that first reaction, reactivity towards hydrogen. Reactivity towards hydrogen. React towards hydrogen. So they react with halogens, react with hydrogen to give hydrogen halide. Halogens reacts with hydrogen to give hydrogen halide. To give hydrogen halide. So I'm taking a hydrogen halide general representation HX. So here X is equal to fluorine, chlorine, bromine, iodine. Then what are the possibilities we can expect here is in the case of HX, then the first possibility is HEF, the second one is HCl, then HBr, then HI. So these are the hydrogen halides. Now let us look at some properties of these hydrogen halides. That first one is bond length of HX. Bond length in that HX bond length. HX bond. So while moving from top to bottom, size of atom is increases. As a result, HX bond length is going to get increases. Then what we can expect is HF is less than HCl is less than HBr is less than HI. So this is the order we can expect. So what is the reason behind it? Because of size is increases. So I will take a small example, HF, then HCl, then HBr, then HI. Look at this. So while moving from top to bottom, the size of halogen atom is going to get increases. The size of halogen atom increases, the bond length is going to get increases. The increasing of bond length, HX bond length, because of increasing of size of halogen atom. So simplest reason is size increases and bond length. Size of atom, the size of halogen increases, bond length increases. The size increases, bond length is increases. This is the first one. The second one is bond dissociation enthalpy. HX bond enthalpy, HX bond in kilojoules per mole, right? So while moving from top to bottom, atomic sizes are increases. Atomic size increases, break the bond required a less amount of energy. We can break this bond very easily. So breaking is very easy. So size is fluorine size is shorter, so bond HX bond is very shorter. Breaking that bond required more energy. So bond length shorter, breaking required more energy. Bond length increases, then breaking up that bond required less energy. So while moving from top to bottom, bond dissociation enthalpies are decreases because of size is increases. So what is that we can expect is HF to break the HF bond required more energy when compared to the HCl is greater than HBr is greater than HI. This is the order we can expect. So what is the reason behind it? This is depends upon size. Size increases. Fluorine to chlorine, chlorine to bromine, bromine to iodine, size increases. Size increases. What about the bond length? So bond length is increases. Sorry, bond length is increases. So size increases, bond length is increases. Bond length increases, breaking that bond required less energy. To break that bond, less energy is enough. Less energy is required. That means bond dissociation enthalpy. Enthalpy decreases. Bond dissociation enthalpy is going to get decreases. That means bond length increases, strength decreases, bond dissociation enthalpy also is going to get decreases. Less amount of energy required to break it. So this is a bond dissociation enthalpy. Third one is thermal stability. Thermal stability. So what we can expect is HF is greater than, HCl is greater than, HBr is greater than HI. Then while moving from top to bottom, thermal stability is going to get decreases because of bond dissociation enthalpy is going to get decreases. Bond dissociation enthalpy decreases from top to bottom. Bond dissociation enthalpy decreases from top to bottom, isn't it? This bond required more energy. To break this bond required more energy. This bond we can break very easily. So moving from top to bottom, bond dissociation enthalpy is going decreases. So easy to break this bond. So that means this is less stable, but difficult to break this bond. It is more stable. Then stability decreases. From top to bottom, stability of this HF, HCl, HBr, HI is going to get decreases. HF is more stable. That means HF is more stable and HI is less stable because of bond dissociation enthalpy. Bond dissociation enthalpy depends upon size. Bond length increases, bond dissociation enthalpy decreases. Bond length depends upon size. So size increases, bond length increases. Size increases, bond length increases, and bond dissociation enthalpy decreases. Stability also is going to get decreases. Next, fourth one, acidic nature. So acidic nature, what we can expect? HF is less than, HCl is less than, HBr is less than HI. So this is the acidic nature of these compounds. HF is less than, HCl is less than, HBr is less than HI. So whenever this is added to the aqueous medium, this is a HI bond. HI bond is very long. So because of size of iodine size is very big. So this HI bond is very long. Breaking up this bond is very easy. So this will produce H plus very easily. Here is a HF bond is very short. Breaking up this bond to release H plus is very difficult. To produce H plus is difficult. So that HF is less acidic and HI is very more acidic because of bond size of halogen increases. As a result, bond length increases, then bond dissociation enthalpy decreases. As a result, this HI will lose this HI will, from this HI, H plus will come out very easily when compared to the HF. So that HI is more acidic when compared to rest of the members, HF, HCl, HBr as well as HI. This is the acidic nature order. And fifth one is boiling points. In the case of boiling points, in general, the boiling points depends upon the size. Size increases and van der Waals force increases. Van der Waals force increases. Size increases, van der Waals force increases. As a result, boiling points also is going to get increases. This is the general trend. So what is what we can expect is HF is greater than, HF is less than, HCl is less than, HBr is less than HI. So HI is the high boiling point when compared to the HBr. HBr is more than the HCl, HCl is more than the HF. But one exception is there. Here is HF, it contains hydrogen bonding. Because of hydrogen bonding, what is HCl is less than, HBr is less than, HI is less than HF. Look at this. So HF has a highest boiling point. This trend is not following. Of course, remaining following HCl, HBr, HI is following, but HF is not following this concept. Size increases, van der Waals force increases, boiling points and melting points are going to get increases. Here I am talking about boiling points. Size increases, van der Waals force increases, and boiling points are going to get increases. But HF has high boiling point. According to this concept, it must be low. But reason is due to hydrogen bonding. Due to hydrogen bonding. Due to hydrogen bonding, HF has a high boiling point. Let us look at HF, second HF molecule, third HF molecule. This is the partial negative, this is the partial positive. Partial negative, partial positive. Fluorine is partial negative, hydrogen is partial positive. So this is the fluorine of one molecule, fluorine atom of one molecule and hydrogen atom of another molecule. So between them is a hydrogen bond. Hydrogen bond. Between these two there is a hydrogen bond. So due to presence of hydrogen bond, to separate two molecules required more energy. So to separate these two molecules required more energy, so that boiling point is very, very high. So this is the boiling points of this compounds. Next, these are the reactive towards elements. In that first one is reactive towards hydrogen. We'll get HX. Halogens react with hydrogen to give hydrogen halides. They are HF, HCl, HBr, HI. These are their properties. This is the first one, reactive towards hydrogen. Next, reactive towards metals. Halogens react with metals to form metal halides. Halogens reacts with metals to form metal halides. Metal halides. Let us take an example. Example purpose I am taking magnesium. Magnesium is solid, react with bromine liquid. Gives rise to MgBr2. Sorry. So here is a metal react with halogen to form metal halide. So halogens react with metals to form metal halides. Next, ionic character. Ionic character of metal halides. The order is MF is greater than MCl is greater than MBr is greater than MI. So this is the ionic character of metal halides. Next, covalent character or covalent nature. Covalent nature or covalent character. So in the case of if the metal exhibits more than one oxidation state, the metal is in more than one oxidation state, in that case the metal with higher oxidation state is more covalent than the metal with lower oxidation state. So let us take one example for this case. I am taking SnCl to SnCl4. So here is a metal Sn in the form of +2 oxidation state. Here Sn in the form of +4 oxidation state. Now the question is which is more covalent? So in this case the metal with more oxidation state is more covalent than the metal with lower oxidation state. So covalent character, covalent nature increases. Covalent nature increases simply this +4. +4 is nothing but oxidation number. Oxidation number. Oxidation number increases. So oxidation number increases, covalent character is increases. Oxidation number increases, polarizing power also increases. Polarizing power. Polarizing power increases. So oxidation numbering, oxidation state increases, or oxidation state. Oxidation state increases, polarizing power increases, and covalent character is going to get increases. Let us take one more example. PbCl to PbCl4. Here is lead in the form of +2 oxidation number. So +2 oxidation number. Here lead in the form of +4 oxidation number. So covalent character which is greater? PbCl4 is greater than PbCl2. In this case also SnCl4 is greater than SnCl2. Here is +4, here is +2, here is +4, here is +2. The point is if the metal exhibit more than one oxidation number or oxidation state, if the metal exhibit more than one oxidation state, in that case the metal with higher oxidation state is more covalent than that of the metal with lower oxidation state. So covalent character increases, oxidation state increases, polarizing power is increases. This is the reactivity towards metals. Next, reactivity of halogens towards other halogens. So halogens react themselves to form a compounds known as interhalogen compounds. What is my point is so fluorine, chlorine, bromine, iodine. So fluorine react with chlorine, and fluorine react with bromine, fluorine react with iodine, and chlorine form the compound with bromine, and chlorine form the compound with iodine, and bromine form the compound with iodine. So halogens themselves react each other to form a compounds known as interhalogen compounds. Interhalogen compounds. Interhalogen compounds. Let us take some examples that there are different types X dash. Here X is equal, all the cases X is equal to large size halogen. X is equal to large size halogen. X dash is equal to small size halogen. X is equal to large size halogen, and X dash is equal to small size halogen. Suppose if you take F and Cl, so you can get a ClF. So Cl is the large size, fluorine is the small size. X dash type, and I'm taking second one is X3 dash, and next one is X5 dash, and X7 dash. So these are the different types of interhalogen compounds. So X dash, X3 dash, X5 dash, and X7 dash, where X is the large size halogen and X dash is the small size halogen. So these are the interhalogen compounds. Halogens react themselves to form a compounds known as interhalogen compounds. They are different types: X dash, X3 dash, X5 dash, and X7 dash. So X is the large size halogen atom, X dash is the small size halogen. So this is reactivity of halogen towards other halogens.